All right, good morning, good afternoon, ladies and gentlemen. We are going to be going over, yet again, some more AP Taylor polynomials. But more specifically today, we're going to be talking about derivatives and integrals based around the Taylor series functions and a series that kind of go from there. So we're actually going to start off with a theorem today. So a theorem. So we're going to say if a function given by, and this is going to be f of x is equal to a sub 0 plus a sub 1 parentheses x minus c plus a sub 2 x minus c to the second power plus dot 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 is going to be equal to the summation when n is equal to 0 goes to infinity of a sub n parentheses x minus c to the n power has a radius of convergence capital R is going to be greater than 0, then the interval parentheses c minus capital R and c plus capital R. F is differentiable. I'm not going to write the whole thing out. So differentiable. And then moreover, the derivative and antiderivative of f are as follows. Number 1, f prime of x is going to be equal to a sub 1 plus 2a sub 2 parentheses x minus c plus 3a sub 3 parentheses x minus c to the second power plus dot 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 dot. Now we can kind of see a pattern that's happening here, right? If we end up doing a derivative of the original function, right, we know that the exponent brings it down, the constant down in front, just like as we see here, right? Well, the constant for x minus c would just be a sub 1, then 2, 3, and so forth. So we end up getting the following summation. N is equal to, now we're not actually going to start at 0 this time, but we're actually going to start at 1 because the first term is a sub 1, not a sub 0. And goes to infinity of n times a sub 1 parentheses, or excuse me, a sub 1, a sub n parentheses x minus c to the n minus 1. So it's almost like that we took the derivative of, in a sense, this right here. Can I do this here? No, I can't during the presentation. So it's like that I took the derivative of it, I brought down the n and then decreased the n by 1. But the only thing here is that this specific term right here is still going to be a sub n, regardless if I start at 0 or I start at 1. Okay, number 2. Then I can say that the integral of f of x dx is going to be equal to c plus a sub 0 parentheses x minus c plus a sub 1 parentheses x minus c to the second power over 2, and then plus a sub 2 parentheses x minus c to the third power over 3, and then plus dot 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 dot, and that continues on to be c plus the integral of n is equal to 0, goes to infinity, of a sub n parentheses x minus c, and then this is going to be n plus 1 over n plus 1. So the only thing really kind of that changed here was, right, that we have our specific constant, constant of integration. But pretty much we still start at 0 for the n value. I know that the exponent right here, right, is going to be increased by 1, and then remember we also put it over the denominator. So pretty kind of standard when I'm doing either the derivative or the integral of some type of power function. Now, this next line, you need to make sure that you know this. Okay, so please make sure that you write this down or just make sure that you remember it. So it says the radius of convergence of the series obtained by differentiation or integrating a power series is the same as the original power series. So that means that my radius of convergence, whether I take the derivative or integral of, it still will have the same exact radius of convergence. But on the other hand, the interval of convergence may differ. I think it's, oh, there's two R's. May differ as a result of the behavior of the endpoints. So the radius of convergence is exactly the same, but the interval of convergence may be slightly different based around its specific endpoints, whether they are inclusive or exclusive. So let's start off with the first one, our first example. So if I give you good old f of x is equal to 1 over 1 minus x, our specific Maclaurin series for this, the first four non-zero terms and the general term should look something like this. F of x is equal to 1 plus x squared plus x to the third plus so on and so forth. And we know that to be a geometric series. And then also the general term is going to be x to the n. Let me clean that up. X to the n. Now, since we know that this is a geometric series, we can also think about this as, right, a is equal to 1, r is equal to x, and we know that the only way that a geometric series can be convergent is when, in a sense, the absolute value of r is less than 1. So I'm just going to take that r and replace it with x, so the absolute value of x is going to be less than 1, so it will be negative 1 is less than x, which is less than 1. So this is the radius. Well, we could say the radius of convergence is 1, and then we can also say that this is going to be converges, someone just say converges for negative 1 to 1. Also remember, we're not including negative 1 or 1 for this case. Now, I'm going to still kind of keep that in field of view, so f prime of x is going to be equal to, well, so I'm going to just work on each one. So 1, well, derivative of 1 is just, well, nothing, so that's 0. This is 1. This is going to be 2x. This is going to be 3x squared, so on and so forth. So this is going to be 1 plus 2x plus 3x squared plus 4x cubed plus dot, 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 dot. And then plus n times x to the n minus 1 plus dot, 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 dot. Now, if I'm actually trying to figure out, does this series converge? Well, since the original one converged from negative 1 to 1, this one is also going to converge. So this is also going to converge from negative 1 to 1. So the thing that I need to test here for this is I need to test to see if, in a sense, 1 works or negative 1 works. So if I, in a sense, do this, ready? So if I throw in when x is equal to, like, let's say, negative 1. So this is my test. So that means that I get, in a sense, the series, so f prime of x is going to be equal to 1 plus 2 plus 3 plus so on and so forth going up. Actually, no, it's actually going to keep going back and forth when it's negative 1. So this is going to be negative here, positive here, negative here, positive here, negative, well, so on and so forth. And you can probably see what's happening here. We can see that this one actually is going to diverge because it doesn't actually, it doesn't go to 0 because the terms don't go to 0. So you can use the nth term test. So the nth term test to prove that this specifically diverges. So that one's out. So -1 doesn't work. Let's choose x is equal to 1. So this is going to be f prime of, well, in a sense, I'll say 1, and that's going to be 1 plus 2 plus 3 plus 4 plus 5, so on and so forth. And that's also going to be exactly the same as that thing. This is also going to diverge. So we can say that this is the only interval of convergence that we have specifically for the derivative of 1 over 1 minus x. Okay, so I'm going to give you a problem, and I want you to try and figure out the sum based around the previous example. So this is going to be 1 plus 2/3 plus 3/9 plus 4 over 27 plus ... plus n over 3 to the n minus 1 plus ... Okay, so I fixed up this problem a little bit. It was kind of off the lines. So if we look at this and see in how the values are changing, right, I can see that the number itself, the denominator, is changing by 3 each time. And if I look actually back up at the previous example, right, this derivative, we can see that the x value does change by each time, right, but it's just going to be 1 less than the derivative, or 1 less than the original. So, and then we know that there's going to be some type of constant that's changing by 1 unit. If we take a look at this, right, 1, 2, 3, 4, we can see that those are my constants. So actually, this right here is actually going to be f prime of, and then this looks like that's actually just going to be 1/3 because of the 3 that's here, and technically there is a 1 here. I can also rewrite this as plus n parentheses 1 over 3 to the n minus 1, which in a sense gives me just, well, you know, this type of series. So if I know that f prime of 1/3 is going to be my answer here, what I can do here is I can just kind of redo this backwards. So if I know f of x is equal to 1 over 1 minus x, I can do, in a sense, the derivative of this. So that's going to be f prime of x. Actually, before I do that, I'm going to rewrite f of x is going to be equal to parentheses 1 minus x to -1. I know it's been a while since we've done actually old-fashioned derivatives. So we're going to do f prime of x is going to be equal to, bring down to -1, parentheses 1 minus x to the -2, and then times by -1. So the negatives actually do cancel each other out. So f prime of x is going to be equal to 1 over parentheses 1 minus x and squared. And then if I know that this answer is just going to be the 1/3 version of this, I just plug this in. So f prime of 1/3 equals 1 over parentheses 1 minus 1/3 to the second power. So it's going to be 1 over parentheses 2/3 to the second. Flip it or bring it up. So this is actually going to be 9/4, and 9/4 is going to be your answer. So we have to do kind of a lot of number manipulation and being able to see what this series looks like in terms of trying to figure out what its sum actually is going to be, right? We can't actually figure it out just by, you know, adding all the numbers together. If they want you to figure out the sum, they want you to either figure out whether it's the derivative of something, the integral of something, or the original function going backwards. So that e to the x, sine of x, and cosine of x, and then also this one, 1 over 1 minus x. Those are the ones that you need to memorize. The next one, I'm going to rewrite the series again, just so that I have them available. So f of x is equal to 1 over 1 minus x, which is going to be equal to 1 plus x squared plus x to the third plus x to the fourth plus ... Remember, this converges from -1 to 1. Okay, what happens if I were to ask you, what is the Maclaurin series, right, centered at 0, of the integral from 0 to x of f of t dt. And so really what we're doing here is we're doing the integral from 0 to, in a sense, x of parentheses 1 plus t squared plus t to the third plus so on and so forth, plus t to the n plus dot 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 close parentheses dt. And if we work out each individual term in this series, we would end up getting something that looks like this. So derivative, integral of 1 with the variable is just going to be t. So it's going to be t plus t squared over 2 plus t to the third over 3 plus t to the fourth over 4 plus dot 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 plus t to the n plus 1 over n plus 1 plus dot 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 dot. And then remember, since we're doing some type of definite integral, we're going to be going from 0 to x. Okay, I don't need to worry about the 0 because, well, if I make every single one of those terms 0, well, then they're just all going to be 0. So I'm just going to now replace them with x. So that's going to be x plus x squared over 2 plus x to the third over 3 plus x to the fourth over 4 plus dot 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 plus x to the n plus 1 over n plus 1. And then that's going to be, in a sense, my series. Now, I do know that it is going to converge from -1 to 1. But I don't necessarily know if the endpoints are actually going to work as well. So, yet again, we're going to test them. So let's test, let's say, -1. So if I look at how this works, right, I'm going to do the integral, or the summation, when n is equal to 0, goes to infinity, of -1 to the n plus 1 over n plus 1. Okay, just kind of quickly looking at this, we can see that this is an alternating series, so that's kind of cool. So since it's an alternating series, we can use alternating series test. So it alternates. Does it decrease in value? Well, if I keep increasing the n value in the denominator, right, it still ends up giving me a smaller and smaller number. And does it eventually go to 0? So the limit as n goes to infinity of, in a sense, the specific type of function, the limit does actually go to 0. And so, right, we can actually say, because of alternating series, that this actually does converge. So we're going to have to go back to our inequality right here and put a less than or equal to -1. So that does converge. Let's check to see if it is actually going to be equal to 1. So n is equal to 0 goes to infinity of 1 parentheses n plus 1 over n plus 1. Now I can say right here that I can actually just disregard the top part. So this is going to be the summation as n is equal to 0 goes to infinity of just 1 over n plus 1. Now, kind of quickly being able to figure this out, we know that it's very, very close to the harmonic series, and we know based around p series specifically, that if the exponent is, in a sense, 1, we know that it's going to be divergent, but we have this plus 1, so we know that it's going to be slightly smaller than just the harmonic series. So what we can do is we can do limit comparison. I want to say we can do limit comparison. Oh, that's interesting. So we can also kind of take a look at it like this. If we go back to here, you can take a look at the term before this is actually going to be the x to the n over nth term. So we can actually look at it not just based around the n plus 1 over n plus 1, but we can actually take a look at it as x to the n over x to the n. We would just start at a different specific term, the sum. So I can actually rewrite this, but we can still say that this is actually going to be divergent. So let's say that I can actually do, I could have done limit comparison test. I could compare it to 1 over n. Actually, you know what? I'll just finish up with that. So I'm going to say the limit as n goes to 0. So remember, I need to make sure that this is going to be, no, it's not 0, it's infinity. So the limit as n goes to infinity of, then I'm going to do 1 over n plus 1 over 1 over n is going to be equal to n over n plus 1. And then so we would actually say the limit as n goes to infinity, we would say that that's going to just go to 1. And since that is going to be, if it is going to be equal to 1, oh my gosh, I'm now having a brain fart when I'm dealing with limit comparison. I think when it is equal to 1, it is divergent. When it's greater than 1, I think. 1 or greater. Anyway, so this is divergent. So multiple ways, right? I could have actually used this and also said that it's going to be divergent that specific way because of p-series, or I could do limit comparison as well when it is equal to 1. That is only when it is a ratio test. That's when it's inconclusive, based on when it's equal to 1. Okay, so, and then the last part. Then find the sum. Okay, 1 over 3 plus 1 over 3 squared times 2 plus 1 over 3 to the third times 3 plus 1 over 3 to the fourth times 4 plus dot 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 plus 1 over 3 to the n plus 1 times parentheses n plus 1 plus dot 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 dot. Okay, before I start to do this summation, I'm actually going to go back to something I kind of mentioned before. So when I'm doing limit comparison tests, right, I do compare, in a sense, some type of function that's really closely tied to, in a sense, the series that I'm trying to figure out the limit for. In this case, is I'm comparing it to some type of series that I know diverges. And so I know 1 over n diverges because it's a harmonic series and p-series. And I know, and when I do the limit and I'm comparing them, I get 1. If that is greater than 0, then I know that specifically if this diverges, so does that diverge. All right, just to kind of clarify things. So it's not just necessarily that since it is equal to 1, it could actually be equal to any type of positive number. And as long as the series that you're comparing it to is divergent or convergent, that other series will also be the same types of, whether it be convergent or divergent. All right, let's get back to this one. So if we take a look at how this problem works, right, this is actually just a version of, in a sense, the previous problem that we just had. If we see here, right, the value that's changing each time, in a sense, is this whole like n plus 1. And we see that there is going to be this 3 to the n plus 1. So wherever the x value is going to be, that's really kind of what we're trying to figure out. So this is actually going to end up being the integral from 0 to something f of t dt. And what is it actually going to be going to? It's going to be actually going to, well, 1/3. Because if I see it how, in a sense, the x value is changing, if I look back up here, right, the x value is changing, in a sense, the exponent on the bottom, right, it's going to be changing by 3 on the bottom, or just, we can also think about that as 1/3. Also, the first term usually gives it away as well. So we're really trying to figure out the integral from 0 to 1/3 of f of t dt. So that's really saying the integral from 0 to 1/3 of 1 over 1 minus t dt. So the original function, doing the integral of that. So if I do this, ready? So I'm going to do u substitution. So 1 minus t is going to be my u. Therefore, du is going to be equal to negative dt. And so I'm going to get the integral from 0 to 1/3. I'm going to convert the variables back, so I don't need to convert the 1/3 as well. So I'm going to get 1 over u du. And so that's going to end up giving me ln. Oh, but don't forget about there's a negative actually out in front. So negative ln of absolute value of 1 minus t. and then we're going from 0 to 1/3. Now with this, I'm going to plug in my values. So I'm going to plug in negative ln, absolute value of 1 minus 1/3, minus, and then another negative, so that's going to be plus, ln of absolute value of 1 minus 0, which is just going to end up giving me 1. So this is really just going to end up giving me negative ln of 2/3. And so that could be my answer, or I can even actually write it as ln of 3/2, because I could bring this up as a negative exponent, and so I end up getting two different values here. All right, I hope this video was helpful for you. Please, if you have any questions or comments, please comment on my Discord or Google Classroom or anything of the sort. And thanks for watching.